Welcome back. Now, if you remember last time, we might have had just a small fire. Well, actually more of a glow when we put a battery to some wire wool. Did you find out what temperature metal iron actually burns at? Surprising, isn't it? Well, to sort of take this a little bit further, what we're going to do now is I'm going to have a small explosion in the corner of my garden. Now, to make an explosion, all I need to do is take that organic material, and it's cotton wool actually, it's very lovely. You feel, oh, so nice. And we're going to put it in an enclosed space. Now, normally when things get hot, well, they have too much energy. That's how things work. So what I'm going to do is I'm going to turn that around, and I'm going to get you to think about when things get hot, when you squeeze them. Firstly, let's try with your hands. Just rub your hands together. You get a little bit of friction, don't you? Now this time, press really hard and rub. Does your hands get hot, don't they? That's because of friction. Now air is exactly the same. If you squeeze air, then the molecules that make up air, they bang into each other. When they bang into each other, they sort of get a little bit excited. The thing is, when we squeeze them all together, they bump into each other a lot more. And when they do that, well, they get a little bit hot and bothered. Think of it like this. How many people fit into your classroom at school? Maybe 30. Probably not even that now, but about 30. I'm guessing you've got quite a lot of space to be able to sit and have your own personal space. Let's hope so. Think though about what would happen if you had 300 people in there. Ooh, would it be a bit tight? Would you be bumping into each other all the time? What about if we put 3,000 people in that room? That's a lot of people, isn't it? So the problem here is that you would all be bumping into each other like this, and you'll get all hot and bothered, and the teacher would make you go outside in the playground. If you're lucky. Well, air is the same. So what I've got here is something called a fire piston. I will show you how it goes together. It's really, really quite simple. That goes in there, and it seals quite nicely at the bottom. That's important to remember. And then the top goes in, and it makes a seal at the top as well. So when you squeeze it, the air inside, well, those molecules get closer together and they bump into each other a little bit more than they would normally. Think about when you pump up the tyres on a bike. If you pump up the tyres on your bike, then what happens is actually the tyre starts to feel warm. And that's because the air inside is becoming compressed. And that word compressed just means it's squeezing it together. So that's what we're going to do with this. The difference is I'm going to squeeze it really fast. And at the bottom, just there, I'm going to place a tiny little bit of organic material, just a tiny bit of cotton wool. Now remember, we said that we needed 3 things for fire. We need fuel. Well, that's great, that's my cotton wool, that's already there. We need oxygen. That's fine as well. The other thing that we need now is some heat energy. Now this energy is going to be provided when I squash this piston down and squeeze that tiny little bit of cotton wool there. Now the air is going to get hot. So what do we think is going to happen to the cotton wool? Good. Now inside here, we're going to start a small fire. The difference between a fire and an explosion in this case is that the fire is going to be trapped. And it's going to be, all of a sudden, a release of energy. All that hot gases, the small fire, remember, is going to force out the piston. So, are we ready? We're going to need a countdown. Let's get on with this. 3, 2, 1. Oh, the whole camera is shaking. Wow, did you see it? Did you see that small fire? Happened very quickly, didn't it? Let me just take this apart and have a look. In fact, if you look carefully, there's a little puff of smoke there. If you look carefully, you can actually see where the black bits are, where it's burned. Should we do that again? But this time, I'm going to do it in slow motion so that you can see it a little bit better. Right, I'm going to slow it down by 4 times. And we'll have a countdown. 3, 2, 1. Did you notice that that small explosion was enough to send the piston, quite a heavy metal piston, out of the top of our device? But that's really interesting. Just because the air gets hot, why should the cotton get hot? Think of this as just like the wire wool that we had earlier. Very, very thin strands of material. Now, as they sort of take on a little bit of energy, remember that they aren't like gases. Gases are well spaced out. There's lots of space for them, and occasionally they bump into each other. In a solid, that's not the case. In a solid, the atoms that make up the material are very close to each other. They're very close to each other. And so when that extra energy comes and they start to vibrate even more, well, sometimes it's just too much for them. So what you actually witnessed here was something called the auto-ignition temperature of cotton wool. Now that's your homework for the next time. Find out what the auto-ignition temperature of wire wool is. That's the temperature, basically, that this stuff just gets so warm that without fire, it just starts ablaze. Right. Now for the next one, what I'd like you to do is go into the cupboard under the stairs or your toy box or whatever, and I'd like you to find firstly a balloon. Yes, it doesn't have to be blue. And I'd also like you to find a bamboo skewer. Something long and thin and preferably pointy. Can you do that? Right, we're going to examine some materials in the next one. So, from me, that's it for now. I will see you again in a short while. Bye!